anyway. All right, so I looked at the problems, which one was it? The last one on the assignment yesterday. And sure enough, it was just the next section that I made notes for today that explained how to do it. And it was exactly what I had been thinking we needed to do without having the equations easily at hand. So hopefully when you went back and had the additional information, you could do problem 4 and problem 9. And if not, then I'm happy to work through those today. I also noted when I was working my way through, I'm trying to put, do my keys close to when I assign the problems, or at least to like plot them out. Homework 19 still has some concepts that are on the next half of the video. So I posted the part 1 of the non-standard state, and then the part 2 with the non-standard state will have more content for assignment 19 on it. So
is it assignment 19 for tomorrow or for today?
It's for whenever you get it done.
Okay.
So, since I'll probably post that one tomorrow morning, I guess it's for tomorrow. So, I mean, you can give it a try if you want. And, it's not that different from the non-standard state. It just uses a slightly different equation, but you don't have to feel like you have to do it. I want to make sure that people take their time with these because this is some pretty different content. For us, I mean, all of us, this is a totally different kind of calculation than what we've done. I've never done this in any of my chemistry classes before. So I know it's taking me some work to, to get comfortable with writing out the problems. So if we want to just work on those some more from problem set 18, we can do that. Or
yeah, I'm good with that. Going over, I think 4 and 9, the ones we didn't do very well yesterday.
Mm-hmm.
Yeah.
All right. Yeah, no, I could see right away that problem 4 was a mistake to have put on before I had that rest of the content. Excuse me. But I'm also feeling awkward because I ran out of regular white paper today and had to go to lined paper. So everything looks different when you do that. All right, problem 4 said that we have PCBs being transported through the environment in the vapor phase to Lake Superior. And we're going to assume that the flux is almost all due to rainfall, which has an average concentration of 30 nanograms per liter.
Okay, I got in late. What are we doing?
Oh, we're just looking at problem 4 from homework 18.
I think I got that figured out.
Good. Well, we're going to work through it.
Okay.
And then we're going to look at problem 9, because that one was also one of those that I had said yesterday, I think we need some more information. And sure enough, we did need more information, but now we've got it. So we're all set.
Oh, okay.
All right. So we have the depth of Lake Superior. We've got the average rainfall. And then we have the residence time of 3 years. So when I worked out this problem, excuse me, I started by writing out just all of the pieces of information I had. So my rainfall had a concentration of these PCBs of 30 nanograms per liter. And the flux was due to rainfall. And I wasn't sure if I was going to need that information, but I figured I'd write it down anyway. The depth of the lake was 150 meters. The rainfall was 80 centimeters per year. So
and that would be flow, right?
Yeah, that seems like a flow, right?
Okay.
And then my residence time was 3 years. And I wanted to know, what is the concentration of the PCBs lake? So I started by thinking about my different equations. So I know that my flux was equal to the flow over the area. I wasn't totally sure what I was going to do with that yet. And then I thought about the concentration being the amount of stuff over the volume, and also my amount of stuff can be the flow times the residence time over the volume. So I thought I probably need to have the volume. And I don't have the volume, I have just the depth.
Well, can't you find the volume for it?
Well, only if I know how big Lake Superior is. So I actually looked back in the problem, or in the chapter, and we had another problem involving Lake Superior. And they gave us the surface area, because the surface area times the average depth, that would give us a volume. But then I did it and I thought, wait a minute, I didn't actually need that. So let's see why we don't actually need that. So the first thing that I was gonna do is actually try and get some information here about the flow, right? Because I apparently need to do something involving flux, so I went ahead and rearranged that. So I said, okay, my flow is equal to the flux times the surface area of the lake. And that's going to be the concentration of the rain times the rainfall rate, which is really the flow, right? Times the area of the lake. So the numbers that we had for these, if we were ready to plug them in, which we're not quite yet, but this is 30 nanograms per liter, and the rainfall rate is 80 centimeters per year. So it's sort of a different way of thinking about, not this one, this one.
Can't we convert, because I converted the 80 centimeters a year into liters per year.
No, this is centimeters, not cubic centimeters. So if it were cubic centimeters, then that would be a good plan. But this one, this is a distance, and that's why we can use it here with the flux, because the flux was equal to the concentration times the distance that the concentration moved, and that's this 80 centimeters per year thing.
Yeah, but none of those units are going to cancel out.
Oh, just wait for it.
Oh, okay.
It'll be pretty. It'll be pretty when it does. So let's go back and think about this volume. So this volume we got from the surface area, right? Times the height or the depth. So volume would be equal to area times depth. So our concentration, which is what we really want, is this stuff over the volume, or the flow times the residence time over the volume, or really the flow times the residence time over the surface area times the depth. Okay? Is everybody buying this volume thing?
Okay.
Yes.
All right. So now we can see, well, hang on. Over here, our flow had concentration of rain, rainfall rate, and area. So on the top, I'm going to have the concentration of the rain, the rainfall rate, I'm just going to write it as D over T, and the area. And so I could figure out, or I could go back and look in the problem, in the chapter, you know, that other problem, and find the surface area, but they're going to cancel out. So I don't have to have them. And now I just have all these numbers. And boom, I'm ready to go. So what's our numbers? We've got 30 nanograms per liter. We've got 80 centimeters per year. We've got a depth. Oh, we forgot the tau. Sorry, I dropped it by accident. So we also have the time. Time was 3 years. And now the depth, 150 meters. So let's check out our units. Years cancel right away. Centimeters and meters, I can make that work. Which way should we go? Should we cancel meters or should we cancel? It doesn't matter. 100 centimeters is equal to 1 meter. So our meters cancel and our centimeters cancel. And now we have a unit of nanograms per liter, which we may not want to stick with nanograms if this ends up being super big, but we have a concentration unit left over.
Well, I
Is that
think
what it is?
nanograms per liter is what it says in the back of the book on the answer.
It might. So let's calculate it through.
Oh.
I got 0.48.
0.48 watts.
It's nanograms per liter.
Mhm.
Okay, let's check our answer. Yep, that's what they have. All right, so this is problem 4 from chapter 2, assignment 18. Okay, any questions?
Yeah,
about
give
that?
me a sec. I'm trying to. Bigger.
What part is causing trouble?
Trying to figure the flux, because the flux is the concentration time the rate constant, right?
So flux is the flow over the area.
I meant up here where you did the F equals the flux times the area.
Yeah. So I see what you're saying. So the flux, let me pull out my, so many pieces of paper. So if our flux, not plus.
I'm just trying to figure out, because I don't.
Yeah. Yeah.
Oh, I get it. Okay, because you were isolating for the F and not the flux.
Right. So our other definition was that it was the concentration times the speed.
Yeah, that's why I was like, wait. She's using a different.
Right. And so this is the concentration and this is the speed. And so although when we initially read the problem, this 80 centimeters per year sounded like it might be a flux, the reason why it wasn't is because this is a distance. And so it was really easy for us to just kind of like get that confused in our minds, because most of the time when we have a flux, right? So it was the time thing that made us clue into made us think that that was probably the flow. But it was this top thing. This wasn't a quantity of a stuff. Like it wasn't grams, it wasn't kilograms, it wasn't moles or anything like that. It was centimeters, which is a distance. So this is not the flow. This is really the distance over the time, or in other words, the speed. at which the rain falls over a year, which is not really, but that's how we're talking about it. The total amount of rain over a year.
So what we thought was flow wasn't flow. It's
Right. So we initially thought this was flow, but it was not.
it was speed.
It was speed. Hmm.
I gotta put the right little symbol with it.
Yeah, and sometimes it can be a little bit challenging to, to figure out which piece of information is which variable, because the units are not totally consistent.
Yes.
The other day we were using the mass, yesterday we were using the mass of the bear as the volume, right? And that's not the volume, but it is talking about quantity per quantity kind of concentration. So from that standpoint, it is. So sometimes you have to take a step back and like really think about, what's our big picture that we're aiming at. And anyway, it can be challenging at times.
Yeah, the flow and the speed, I had a question about that, but you just answered it.
Mhm.
It also kind of goes along with area and volume. They seem almost interchangeable sometimes.
Yeah, it's that unit difference, right? Area is going to have 2 length units and volume is going to have 3 length units for the 3 different dimensions that it has. So it's
Okay.
going to be like meters squared versus meters cubed.
That makes sense. Okay.
Yeah.
Okay. I think I got it. Okay. To 9 we go.
Any additional questions on this part of the assignment from anybody else who's in our Zoom room? Okay. If we don't have any questions, then we'll go on and look at problem 9. So problem 9 was really confusing last night because we kept on thinking we did not have enough information, and that was true. We didn't have enough information, and the information that we were lacking was the theoretical information that we needed. So what we were talking about last night was that I was saying, look, we're going to need to have some kind of graph that is going like this.
Mhm.
That when we start adding something to a system, at some point it's going to be at a steady state. And it'll have some final concentration that is going to be reflected by this. And we need to have some equation for this to get there. Well, that's what we got today, was we got an extra special equation dealing with these non-steady state scenarios. And so this situation where you start with no stuff, a concentration of 0 at time is equal to 0, then we can use this time-dependent concentration equation.
Oh, I don't remember that on the video.
It was in the
second one, the part 1 from today.
Yeah, the second one I posted today. It was around lunchtime, I think.
Hold on. I got
Anyway.
oh, I didn't get the non-steady state one. I stopped at the flux and flow one. That's why.
No worries. There will be plenty to keep you busy for tomorrow.
Uh-oh, what does that mean?
Well, I mean, this will be plenty to keep you busy for tomorrow. So, and then I'll post the second half of this and you'll be ready to just segue. It's not a super long video. I could have covered both of them in one, but I'm like, no, I'm going to try for shorter videos and see if that's helpful for people. So I think
It is. Thank you.
Is it? Okay.
Yeah.
My Moodle just updated. I didn't see it before I started this Zoom. That's why I was like, wait, there's another video?
There is another video, but it's
okay.
fun. You get to wait for it for later. Yay. It'll be exciting. So anyway, so the information that we are given in problem 9 is that we have a soluble pollutant dumped in a clean lake starting at day 0. The rate of the increase, that would be K, is 0.069 per day. We're going to plot or sketch a plot. We know it has this general shape. We want to know what fraction of
I think we lost her.
Yeah, we did.
I did just get kicked off. Okay. Well, we'll pick that right back up. All right. So we've done a number of these problems that are kind of similar when we were doing integrated rate laws. Then, okay, sorry, I just caught my Wi-Fi thing and thought it was flaking out again. I'm just suspicious of it now. All right. So we've done a lot of this talking about a concentration now in terms of a concentration at some other time. And so in the past, what we've done is we've talked about what's our concentration now after 10 days compared to our initial concentration. And so in that case, we were doing things like the first order rate law and calculating half-lives and things like that. So we are going to express our concentration just the same way. We're going to say it's some fraction of Cmax. It's some constant multiplied by the Cmax at 35 days. And we don't know what X is yet, but the good thing is that if we can relate our concentration at time t to the Cmax, we can now cancel them out, right? Check it out. So if our concentration at time t is a constant times Cmax, then that's equal to Cmax times 1 minus e to the minus kt. And I can divide out the Cmaxes and they'll just cancel. Now I have that my unknown is equal to 1 minus e to the minus kt. And I have k and I have t. So let's plug it in.
I don't know if that's right.
Is it less than 1?
It's like 0.91.
I got 0.91.
Yeah.
Cool. Sounds like
What
we
would
have at least
be-
2 people.
What would be the unit?
So it isn't a unit, it's a fraction.
Oh.
Right? So what it's saying is that my X value, or excuse me, my concentration at 35 days is equal to 0.91 times my maximum concentration. So after 35 days, I have reached 91% of my maximum concentration. So if we go back over to our graph, this is our maximum concentration, right? So 91% of our maximum concentration is, I don't know, maybe like there or something, 0.91 of Cmax. So this is at 35 days. So that means that right here, this must be 35 days. So we can just fill in the rest of our graph accordingly, our sketch, you know. I mean, maybe this is 10, 20, 30, 40.
So that would be where the curve would peak then.
This would be where the curve would hit 0.91 of the maximum. So we have to be, most of the way up to our maximum value, which I eyeballed as being right here, right? And this really is intended to be a sketch. It doesn't have to be super fancy. If you really want to be fancy, you can graph it in Excel. So, you just would pick, excuse me, a Cmax value to use, and then you would calculate the C of t value based on the Cmax. But you don't need to. That would be overkill for this problem. Just a sketch is fine.
Okay.
And this calculation, it being 0.91.
Okay. Does that mean we could maybe do one problem in assignment 19?
Of course. I don't mind doing problems in assignment 19. There's just content in assignment 19 that's in the video I haven't posted yet. And so,
okay.
So I almost took it down this afternoon. And I was like, well, I don't know. People probably already saw it, and then it'll just be confusing and like, oh no, Moodle is malfunctioning if they can't see it. And so I decided not to, but I'm happy to talk.
Well, no, if I need to watch the other video, I'll watch the other video.
Yeah. I mean, we can also just grab another problem that I haven't gone through.
I have a couple questions about the video.
Please.
Okay. See, on the non-steady state mass balance one, part one.
Let me grab my notes. Yeah.
I described this to you, but it's you're at the question, how long will it take for the lake to reach 150 ppm? And you were doing that Cmax equation.
Okay.
And you looked to the part where it was 150 ppm divided by 280 ppm. And it was 1 minus e to raised to the negative kt. Then you converted it to e raised to the negative kt. And then somehow it looks to me like the 1 minus, the e, it switched to the other side of the equal sign, but it stayed 1 minus.
It's always possible that I wrote it down wrong in the video, but let's see if we can't get to that place. So in my notes, I C of t is equal to the Cmax. This is our overall equation. And then our current concentration is that 150 part per million that we're looking for. And our current concentration is our maximum concentration is a 280. And so then I divide them out. 150 over 280 is equal to 1 minus e to the minus kt. So far, so good. Is that looking like what you have in your notes?
Exactly, yep.
Great. So then I am going to add e to the minus kt to both sides. And I'm going to subtract 150 over 280 from both sides, which I didn't show. And that means I'm going to get e to the minus kt is equal to 1 minus 150 over 280.
Okay, that's exactly where, yep, I see it now.
Okay, yeah, no, I just skipped the step in the video. I'm happy to go through stuff like this.
I have another question about the flux and flow video. Specifically, example number 3, the multiple sources of pollutants.
Let's see, flux and flow. Example 3. Okay, so this was the one with the wet and the dry sources, is that right?
That's correct.
Okay, so this was the Lake Superior example, which is where I was like, I feel like we had a surface area for Lake Superior. Yep, we did.
Exactly.
Okay, so was it the rainfall part, or was it the dry settling of the particulates part, or just everything?
So it's kind of the same question for both parts, but it's under the starting with the F of rain. How
Okay.
did you? Yeah, how did you cancel out the kilometers squared as
Oh,
far as the
okay,
unit?
sure. So when I set this up, I have my concentration times my area times my speed. And so those numbers, 2 nanograms per liter, 8.21 times 10 to the 4th kilometers squared, and 80 centimeters per year. Right. So when we do the unit conversion on this one, I opted to put everything into meters, I think. Let's see. No, I converted liters into cubic centimeters because then I knew that it would convert here. And so I went from kilometers to square centimeters as well.
How do you do that though? Can you run
Yeah.
it through?
So we'll do each of the parts. So 2 nanograms per liter is probably the easiest one because we know that 1 liter is just 1,000 milliliters, 1,000, not 100. And 1 milliliter is the same as 1 cubic centimeter. So this gets us nanograms per cubic centimeter. So this is just okay, this time, hopefully for sure. So where were we? We were right here where we were converting our kilometers squared. So kilometers squared is like kilometers times kilometers. So I have to convert it twice, one for each of the times that I'm multiplying the kilometer. And then, so I can write that separately, or I can just write it as 1,000 meters over 1 kilometer, the whole quantity squared. So we have to do the same thing when we go from meters to meters. We'd have this twice, so I can square it, or I can write it out twice like I did right here. Does that sound okay so far?
So wait,
Yes.
you're going from meters to centimeters?
Yeah, so I'm going from kilometers, 2 kilometers, 2
Sorry,
kilometers.
you keep going in and out on my end, so I'm not hearing everything.
Sorry about that. Hopefully it'll be okay sound quality on the recording at the very least. So yes, I am canceling my 2 meters with right here because this one is squared. And then I'm gonna have centimeters squared when I'm done.
So hold on. But if okay, so on the first one, back on the 2 nanograms, because you're dividing it by 1,000, it wouldn't be 2 anymore, would it?
No. It'd be 2 times 10 to the minus 3.
And then this one would be, oh, geez.
4, 7, 10, 12, 14.
Yeah, I'm just trying to, yeah.
Yeah, okay. And then that last one was 80 centimeters per year, and we're not going to do anything to it. So we're just going to leave that one alone. So that means that our flow from the rain is 2 times 10 to the minus 3 nanograms per centimeter cubed times 8.21 times 10 to the 14 centimeters squared for the area times 80 centimeters per year for the rate.
Okay. Those go away. Okay. Okay, can you do the work through for the dry, for the F dry?
I'm just going to ask my husband to make sure that our son is not like streaming videos or something like that. All right. So, what did we get? Did everybody get the answer for the rain that we were expecting?
Oh, you did the nanograms to kilogram conversion?
I did in, this one is just grams. In the video, I think it did kilograms.
Uh-huh.
Yeah. So we'll go to kilograms. I just, couldn't remember which way we wanted to go. Okay, so is everybody getting 131 kilograms per year or something pretty close to it?
Okay, hold on. I'm trying to get all the conversions in my notes.
No problem.
Okay, so nanogram.
Yeah, I got 131.36.
Great.
Gram. Okay. Yeah.
Okay, good. Then the dry part of the particulate settling, we start with the same kind of setup where we're looking at the flux times the area, or in other words, the concentration times the speed times the area. And this time, our concentration in the dry air is only 5 picograms per cubic meter. And we still have the same area, 8.21 times 10 to the 4th kilometers squared. And then the speed, depending on where we were in our calculations, I think I had it a couple of different ways. I had calculated as 0.24 centimeters per second, but I'd also calculated it as 7.4 times 10 to the 4. So I don't remember which one I put in the video. Probably this one though.
You put the centimeters per second in the video.
Okay. Well, it does turn out to be the same. If you want me to do the conversion, I can do it.
I do the centimeters per second conversion.
Okay. So
that's in the video.
Yeah, so I can write it out.
Okay.
So centimeters per second. And we're heading toward meters. So 100 centimeters in 1 meter. Seconds, we got 60 seconds in a minute. We have a ways to go. We got 60 minutes in an hour. We got 24 hours in a day. And we got 365. If you want to go 0.24, you can.
Okay.
I didn't bother because we're only keeping 2 sig figs and it's kind of approximate anyway, so it's good enough.
But what doesn't it need to be kilometers, not meter? No. Yeah, it doesn't have to be km, not m, because you would need to cancel out the km and the.
I'm gonna take it to meters over here as well because I have meters cubed here and I don't feel like fiddling with it. But it's totally up to you on which direction you want to convert things.
That's fine.
So yeah.
What's that number? That's gonna be 10. That's a really big number.
Yeah. But it depends on the units, right? You know, once we convert them, we'll have a number that's a little bit more manageable once we go to kilograms per year. So, I mean, this number is going to be
it was big. It's like 7.6 times 10 to the.
Yeah, I mean, it's in meters per year.
4.
Hopefully this first number is 7.4 times 4 to the, or times 10 to the 4th.
What's close?
Yeah, this number is going to be bigger. We're going to have 8.21 times 10 to the 10th meters squared, right?
Okay, hold on.
No, sorry.
Ooh.
Yeah, that's right.
Hold on. Okay, so.
Wait, that's 12. And then for our concentration, we're going to kilograms. And that's going to make everything go a little smaller when we multiply them.
Is that times 10 to the 12 picograms per gram?
Yeah, pico is 10 to the 12th. 10 to the minus 12, depending on what direction. It's 10 to the minus 12 grams is a picogram.
Okay, so. Yeah, it's like really small. Oh, what happened? The screen
I died.
went off.
I didn't die. I just got kicked off again for like the 4th time in a row.
Okay, and this number here is just to the 10th meters squared.
Yeah.
And then that one's like 5 times 10 to the negative 15th is the picogram one.
Mm-hmm.
Am I to assume that most of the problems we're going to be doing are going to have major conversions like this?
They seem to, yeah. A lot of them seem to have a lot of unit conversions. Not all of them. Like on homework 19, I think there aren't as many.
Oh, thank God.
It's just unit conversions, though. We're gonna get really good
Yeah.
at dimensional analysis.
On one of them, you went and you're like, "Here's the answer," and I went, "Okay, fine." And I paused it and I went through and I did all the
Yay!
conversions.
That's what I want you to do.
And I'm like, "Good, too many conversions."
Grumble.
I mean, I am all up for stoichiometry, but Jesus.
Yeah, they can get a little bit much. I don't usually go this far, but you know, when you're dealing with really small numbers like these concentrations, but then you're doing it for a long period of time, and so you have to convert, combine big numbers with little numbers, yeah, with big areas, it just kind of ends up being necessary.
Yeah, I came up with the right answer, that 30.377.
Great.
In the video, you had 30, so that's perfect.
Yeah, I just rounded things off.
Yeah. I have 2 more questions, but if anybody else has one, go ahead.
Is it on the new video that?
I have one general question from Flux and Flow and one specific one from the new video. Okay, so how did you know you could use the particles of lead from example 2 for the BAP over Lake Superior? Like, I wouldn't have made that connection, so.
Let me go back and look at it. Particles of lead. Oh, which problem are you?
It was example 2 for Lake Erie and.
Which video was it in?
Oh, sorry, that was Flux and Flow.
Okay. That is the second. All right. I need more paper clips too. I'm running out of lots of stuff.
Yeah, I'm with you.
Yeah, I'm running out of space in my file folders. Yeah, I've got no more. So I'm gonna pick them up in my office when we go down this weekend. So that'll be good. All right. Okay. So presumably this is this problem. I didn't write down lead anywhere. Was it Lake Erie instead of Lake Superior?
Yeah, Lake Erie was example 2 and it had the lead, and then example 3 had Lake Superior.
Perfect. Okay, so in the the description for how we set up this problem, we said we've got the lake surface, and it has a certain area, and that area was 25,700 square kilometers. And then the other information that we had was that we have 21,000 kilograms per year, which seems like a big number. And because this is a kilogram and not like a meter or something like that, we know that this is a flow number. And then we have a concentration of the lead, and that was 11 nanograms per cubic meter, and that was in the air. Right?
Yes.
So, so the information that we have, we can relate flux 2 ways, right? We know that it is the flow over the area, and it is also the concentration times the speed. And so if we look at the pieces of information that we have the flow, we have the area, and we have the concentration. This is what we want. So it's sort of a matter of trying to find the equations that describe the systems that we have, and then identify which pieces of information we have so that way we can, solve for the unknown. So I just solved for this one. Everybody still there?
Mhm.
Okay. So is that enough detail, or do you want me to go through more numbers?
No, it's more of a general question. Is we use the answer from example 2, the 0.24 particles of lead or centimeters. Then we pulled it over to example 3 for the BAP, or I guess the particles of lead fall under the category of BAP, or?
So this speed, and this is not something I would have just known. It's based on prompts from the book that the settling of solid particles from the air of whatever type all tend to be in this approximate range. And so, like many of the problems that we do in the book, there are some assumptions and approximations that are in there. For example, like we picked the size of the house, or we just, picked the size of the fish or the size of the bear. That we started with a general principle, and then we had to make some assumptions to get things going. So I would not know at what, rate things settle if the book wasn't telling me what rate things settle at. So that's why I picked that number to use in the later Lake Superior problem.
Okay, thank you. Yeah, I didn't catch that in the book, so appreciate it.
Yeah, no problem. I mean, it's, as I said, with material that's so new and so dense and so different than what we're used to, it takes some time. So I'm trying not to speed through. I'm trying to make sure you have enough time to really sort of absorb the content and take your time with these calculations. And I mean, I know what I'm having to do is I'm having to go back and like write down all of the equations that I might possibly need, and then identify which pieces I have and how they can go together. And that's taking me a lot of extra time too. So as I said, I'm trying to not go too quickly, because this is all very new stuff for all of us.
Yeah, I appreciate that.
Yeah, it helps me remember, when I'm doing new things, how it is to do new things. So it's helpful for me as a teacher.
Yeah.
Yeah, and the book isn't very easy to understand. I tried to read the section on this, and I'm like, my brain hurts.
Yeah. Equations. And unless I'm working out the equations myself, my brain just skip over them. I'll be totally honest. I mean, not just in this book, but every single book. This has been my case since forever, like freshman year of college. I just start thinking about my grocery list or something instead. So I have to work it out myself.
For the non-steady state part 1, when you converted the 280 parts per million, I did it the kind of the long way.
Mm-hmm.
And I came out with 2.8, and I know in the video it was 0.28. I can't figure out where I'm going wrong. Is it possible to write that one out the long way?
Yeah, I think so. All right, let me see if I can find that page. Okay, I have too many 0.28s. That was 0.28 days. Non-steady state, you said, right?
Yes. It was example number 3.
Okay. Yes. At least I'm smart enough to number my pages, so. All right, so hopefully I did not make a math error, but it's always possible that I did. So I said, if we have 280 parts per million, this is the same thing as 280 divided by a million. So if I multiply that out, when I calculate it, I get 2.8 times 10 to the minus 4 as the fraction. And I always have to remind myself that this is similar, this is analogous to 0.3 is the same as 30%, right? So 280 parts per million is the same as, this would be the analogous part here. Okay.
Mm-hmm.
So then, are you talking about when we went and converted it to like kilograms to meters per meters cubed or something?
Yes, I was going off of the mass balance and flow that we did. We did it the other way,
Yeah.
from kilograms, meters cubed, all the way to parts per million. So I just worked backwards, and I came up with the wrong answer every time.
Okay. So let's see. I was actually basing that off of, because I was feeling too lazy to go and do it again, one of the earlier videos. So let me pull up that earlier video where I did it by hand.
Yeah, it was under mass balance and flow, under aqueous examples.
Yeah. But 1, 2, where's my other 3 and 4. My pages out of order. They are. I was going to say, there we go. Okay. All right, so let's work it out. So when we did it the other direction, we said we had 8.7, or whichever our number was, times 10 to the minus 4 kilograms per meters cubed. And we were heading toward parts per million. So the first conversion that I did was I said, all right, I remember that milligrams per liter from a long time ago was the same as parts per million. And so I'm going to go unit-wise to milligrams per liter. So kilograms to milligrams, that's a straightforward unit conversion. Just kidding. Now I'm going to do it. Okay. So I just got done converting my kilograms to grams, my grams to milligrams, and now I'm going to take my meters cubed over here to liters. So meters cubed is a really big unit, and I might have a hard time going directly. So what I'm going to do instead is I'm going to remember that 1 meter is the same as 100 centimeters, and then I can cube it. So I'll get 1 meter cubed over 100 cubic centimeters. So that's what? 1 times 10 to the Okay. Tomorrow I'll just go sit at the library and then we won't have this problem because I'm tired of it. Okay, so our density, we can do this whole milligram per liter to parts per million relationship. So that was a long time ago. I forget which video it was in. It was like several weeks ago when we realized this. I think it might have been when we first started talking about atmosphere, or maybe it was just in that parts per million video that I made that was separate. So anyway, if we do our calculation here, we're going to take kilograms per meters cubed. We're converting the kilograms to the grams, grams to milligrams, cubic meters into cubic centimeters into milliliters, and then into liters. So we can start by just canceling out one of the thousands. And now we have 10 to the sixth, which is the same thing as 1,000 times 1,000 in the denominator for this guy right here. So we can cancel another one of those thousands. So this is going to be 8.7 times 10, and I've got a -4 and then another -3. So that was -7, which is milligrams per liter. And when I do my, so this is my fraction version. And when I go from milligrams per liter to parts per million, I have to remember that we're going to multiply by 10 to the sixth. So that would give me 0.87 parts per million.
Yeah, on this one I get 0.087 if I just multiply it all the way out. So I guess I have to keep looking and see what's happening. It's the same problem for the other video.
So what may be happening, depending on how you're entering in your scientific notation, if you are multiplying 1 multiplied by 10 taken to the power 6 in your calculator, it may be adding an extra power of 10. They sometimes do that. And so instead, make sure that you are entering like 1e6 for 1 times 10 to the 6th.
Yeah, I'm definitely a big fan of the E. Has anybody else tried calculating it and see what you get?
Yeah, I did it and I got the 0.87.
Okay.
And I did it just the way she had it written down in the example.
Did you try doing it the long way, like with all the stuff?
Yeah. Because my calculator allows me to put in fractions and I can separate them with the parenthesis, comma things, just like she does.
Yeah, I do that too. Okay.
But isn't it just as easy? Oh, because you're going from milligrams per liter to parts per million.
Yeah, so this was just kind of a blow-by-blow breakdown to remind us of the process that we were going through when we went from this kilogram per meter cubed unit over here. What did I just do? Just want to draw, stop it. So when we went from the kilogram per meter cubed to our parts per million, I didn't want to have to go through this calculation again because I was feeling lazy. So I said in one of those more recent videos that I had 280 parts per million. And so if I just want to go straight to kilogram per meters cubed, I'm going to remember that over here I had 0.87 parts per million, and it was equal to 8.7 times 10 to the minus 4 kilograms per meters cubed, or in other words, if I wanted to just write it the same way, I could say 0.87 times 10 to the minus 3 kilograms per meters cubed. And so if I want to go from parts per million to kilograms per meter cubed, then I can just go times 10 to the minus 3 and simplify it from there if I want to.
Yeah, I found my mistake. I had
Oh,
100 milliliters over a liter instead of 1,000. So I just
Yeah.
carried that same mistake over. So
That's so easy. I
I
have
appreciate
written
you taking the time with this and all the other questions, and everybody else
Yeah.
letting me ask so many.
no
So it
problem.
would literally just be your whatever your parts per million is times 10 to the negative 3, and that would get you whatever your kilograms per meters cubed would be.
Yes, it just happens to work out that way. And this is not a ratio. Okay, this may be just like one too many times for the day. Do we have more questions?
No.
Are we ready to call it quits for tonight?
Yes.
Thank you.
Okay.
And you said we're going to get the other video tomorrow, right? So part 2.
Yep. Yeah, I got about 2/3 of my notes written, and I wanted to write out one more example problem, and then it was.
And then it's just going to be assignment number 19 to finish. Or are we going to get another one?
It's only Tuesday today.
Well,
so,
I meant after the videos, are we going to get another assignment, or is that assignment 19?
So assignment 19 is up there, and I'll probably put at least one more that has to do with what we're talking about here. And then because we don't have a quiz, I'm going to feel a little bit more flexible about how I post the content and the assignments. So I may sort of let the content and the assignment sort of smush into what we talk about next week too, to try and get a head start on some of that content.
Okay.
But since we don't have a quiz, the homework isn't, really due at a particular time. So.
Well, I was just wondering, because you said that assignment 19 more focused on this video in part 2. So if that's true, then assignment 19 goes with these videos. And so we can have another video tomorrow to go with whatever the next assignment is. Okay.
Yes, we will.
That was all I was asking.
Yep, we will. Alrighty. Well, good luck with all of the material. And we will meet again tomorrow night.
All right then. Have a good night.
Have a good night.
Bye.